Mathematics is fun, interesting, creative, and inspiring. I might even suggest it has an element of inventiveness. Do you all agree? Remarkable. Our next speaker thinks so, and will offer proof in her speech. Fibonacci Fun. Please welcome Mary Cyrus.
Fibonacci.
I have some interesting objects to show you. They all look very different, but I assure you, they all have something in common. I have a picture of a flower, and this is a sunflower, and it happens to have 21 petals. I have a Starbucks card, and we also see this same shape with credit cards. It's a very pleasing rectangle. Here's a tote bag with stripes on it. I think these stripes are also very pleasant to look at. And finally, a nautilus shell that has this beautiful spiral that was built as the nautilus grew and grew and grew. So what do all these seemingly disparate objects have in common? They can all be described by Fibonacci sequence of numbers. Ladies and gentlemen, tonight I have the pleasure of explaining Fibonacci numbers to you, why they are creative and exciting and fun, how they make you think, and I hope that they make you think critically. So, let me show you how to spell Fibonacci. I'll let you ponder the sequence while I tell you about Mr. Fibonacci. His name was really Leonardo da Pisa. He came from Pisa, Italy, and he was a mathematician in the 13th century. What he should be known for in our history books is that he introduced the Arabic numbering system to Western Europe, which also opened the door to more commerce and modern algebra. Prior to this, everyone was using Roman numerals, which is okay for counting, but it's very difficult to do any kind of calculations using Roman numerals. So if you were a merchant, you would have to run around and find somebody who could use an abacus before you could do any addition, multiplication, subtraction, and so on. That is what Fibonacci should be known for. And by the way, Fibonacci is his nickname. Leonardo was also known as Fibonacci. But instead, he is known for an obscure sequence of numbers that he wrote in his book, Libra Abaci, Book of Calculations. And it is that by which we know Fibonacci today. What is a Fibonacci sequence? It's an interesting sequence of numbers that you build on, starting with 0 and 1. You add the last two numbers to get the next number of the sequence. 1 and 1 is 2, 1 plus 2 is 3, and 5 and 8, 13, 21, and so on, and so on, and so on. Now let's just look at these numbers by themselves. How do they describe, this purse? When I knit this purse, I decided that I would knit Fibonacci number of stripes. That way, I didn't really have to think much about the design of the purse. I knew that it would be nice proportions and that I would be pleased with it at the end. So I knit 13 blacks, 8 copper, 5 red, 3 green, 2, 1, 2, 3, 5, 8, and 13 stripes. And I think it came out to be pretty nice. I already mentioned that these flowers had 21 petals. Oh look, it's a Fibonacci number, 21 petals. And we see this over and over and over again, very common in nature, that flowers will have a Fibonacci number of petals, and a twig on a tree or a branch will have Fibonacci number of leaves, or that number of lobes. Think of a maple leaf that has 3 lobes on it. The rose bush has either 3 leaves or 5 leaves on its branches. As if that wasn't interesting enough, we can then square each of the Fibonacci numbers. And who doesn't like a nice square number? So those are obvious. 2 squared is 4, 3 squared is 9, and so on. Well, yeah, that's kind of nice. I like squared numbers too, but it gets better. If you can add a Fibonacci sequence of numbers, why can't you add the squares? So we're going to try. And this is what some of the squares of Fibonacci. So we just start with 1 and 1, plus 4 is 6. 6 and 9, the next one is 15, plus 25 is 40, 64. Well, those aren't Fibonacci numbers, but if you look at those products, 6 is 2 times 3. 15 is 3 times 5. 40 is 5 times 8. We see a sequence going here. And 104 is 8 times 13. So we have the sum of the squares as a Fibonacci sequence. Now this actually does help us in algebra. And here we see 135, well, you can see that, equals 104 when we sum the squares. Interestingly, you get the same result if you take the last number in the sequence, multiply it times the next number, and you still get 104. Here's the proof of that. After all, when we have mathematics and numbers, we just use it to describe something that's already found in nature. I'll move this forward here. And this is 1 and 1. Those are 1 squared and 1 squared. And that gives us 2. And so we have 2 squared, which is 4 altogether. These are 1-inch increments. Here we have a cube that we can fit in here. 1 plus 2 is 3. 3, 1, 1 is 5. 5 cubed, 5 squared I mean, and 8, and 13, and 21. This gives us the sum of the cubes, sum of the squares. If I take an arc and start making, if I take a compass and start making an arc through all of these, I end up with what's called the Fibonacci spiral. And that is how Fibonacci numbers can describe this spiral that we find in the nautilus. We find it in a fern frond that is going to unravel, and we find it indeed in the universe itself. My warning about Fibonacci is this: mathematical models only describe something that is already built. They don't actually build anything. There are arguments that Fibonacci numbers are God's fingerprint for having built the universe. But that can't be. There are too many exceptions to it. We have a flower called the poppy, which has 4 petals. The lily has 6 petals. So that argument falls apart. There are also people who use Fibonacci, I'm looking at that light, Fibonacci numbers to predict the stock market trends. And again, this is a fallacy. You cannot use a mathematical number to build something. It just doesn't work that way. It works the other way around. If it's working for people, it's because they are ignoring the failure rate. So I hope you have enjoyed Fibonacci. I hope this gives you something to think about, and that you, like I, think that math is fun, creative, and inventive. Mr. Toastmaster.